What's going on, everybody? Today I want to introduce you to the interactive network, or internet as I call it. So what is the internet? How does the internet work? Alright, I'm not going to call it the internet. It's this interactive neural network. So what is all this stuff that you're seeing right here? So it basically works like this. You have inputs down here at the bottom. They have a value between -1 and 1, and I can just drag them. And the processing works up layer by layer. So this node, for instance, to get its value, it takes a weighted sum of all these input nodes, runs it through a nonlinearity, which is hyperbolic tangent. And you can see, if I hold my mouse over it, there's a little graph of it. So that black dot is the sum going into it, and the output, or the y-coordinate of that dot, is the actual value of the node. Now, obviously when I change an input, it changes this hidden layer, it's called, in a neural network, and when these values change, it's going to change the next layer, and so on, all the way up here to the output. Now, these outputs, you can see their values are all dependent on the neurons that came before them. But I can do something kind of crazy here. So I can actually drag one of these outputs and change its value by dragging, even though its value is completely dependent on all this stuff that came before it. And so what I'm doing is backpropagation. So what I'm doing is giving a small delta. I want to change this value up here. So when I drag the mouse, it's going to look at the position of the neuron and the position of my mouse, and it's going to just try to reach my mouse. So if my mouse is above the position of the neuron, it's going to give a small positive delta. Now I have to bring that through the derivative of the hyperbolic tangent, currently evaluated at the sum of the neuron, and by bringing it through, this is the chain rule, and what I'm doing is multiplying by the derivative of the hyperbolic tangent. It's quite a mouthful there. So I get the delta inside of the sum of this neuron, the weighted sum. And then if I want to change the weights that lead into this neuron, I use the parent neuron's values as how I change it. So to make this make more sense, let's cut down on the number of neurons here. Let's get rid of biases, get rid of these hidden neurons, and just have some inputs and some outputs. Let's have less layers. Let's just have 2 neurons. So when I move the input, it's obvious that the output's going to change, right? Now, the weight from this input to the output is negative. And I can see that by just clicking on this link. So minus 0.46. So when this is a 1, it's going to be 1 times minus 0.46. And it's going to go inside of this neuron. And that's the weighted sum, which then has to go through the hyperbolic tangent, the nonlinearity, right? So because this weight is negative, when this value increases, you can see the output decreases, and when this decreases, the output increases. So they kind of have this play between them, this back and forth. One is always going to be the opposite of the other one. Not the exact, opposite, but they're negatively related. As this goes up, that goes down, and as this gets more negative, that gets more positive. So there's like a negation going on. Now what's cool is, if this is a value of 1, if I want to change the value of this output neuron, the only way I can change it is by changing this link. Because this is an input, I can't change this value over here. So what am I going to do? I'm going to change the value of this link here. So if I want to make this more positive, I should probably make this link more positive, right? Because I've got a positive input, and to make this output more positive, I should make this be a positive number. So we have a positive times a positive will give me a positive up here, right? So if I drag it, you can see that the weight is getting more and more faint. It's getting less negative until it's 0 right here. And then if I keep dragging it, there you go. So the weight is now positive. And red means positive and blue means negative. So if I see what this weight value is now, it's 1.77. And if you see, when I change this neuron, look at the output, it's going to stay in step with this input neuron, right? Because I almost have like an identity. It's just this value, 1 times 1.77 into the hyperbolic tangent, which is almost like a linear function around 0. You can see in the upper left corner there. So that's all fine and good. We can change the input and the output changes, and this is learning. This is backpropagation in neural networks. I can change the output however I like. So if I want a -1 when I've got a 1 down here, I can do that. And there's repercussions, you know. Now the weight is negative, so they have this negative relationship again. So I think that's kind of interesting. I can change the output if I want to. So let's add another layer. So now we have this kind of hidden neuron. So the processing of this network is going to be the input gets a value. It's weighted by this weight, which is random to start with, so 0.3. That's going to go into this neuron and go through hyperbolic tangent. Then this is going to have a value 0.27, which is going to go into this neuron. And this weight is pretty small, but it's a positive number. So really when this increases, the output should increase, and when this decreases down here, the output should decrease. And you can see that they all change their sign. You know, they go from positive to negative all together, which is great. But if I want to change the output, not only now can I change this weight, but I can also change the value of this neuron. And this is true backpropagation. Now we're going layer by layer back through this network. So if I want to bring this value up, let's just think about what needs to happen. Well, if I want to bring this value up, we have a positive weight and we have a positive value coming into the neuron. So because we have a positive value, we should change this link by this positive value. And how else could we make this positive? Well, we could change this neuron's value too. And so how do we change this neuron's value? Well, we should, because it has a positive input and a positive weight, we should make this weight go up and up and up. So let's try it. So you can see that this weight got really huge here, 1.48, and it also brought this intermediate neuron's value up by increasing this weight to 1.2. And I can do the same thing if I want to make this negative. It's going to do something interesting now. So what did it do there? Let's start when it's just slightly positive. So we have a positive weight and a positive input value to this neuron. Now if I want to make this negative, I should make this weight get smaller, right? So I should make this weight get more and more negative. So that's what we're going to do. We're going to drag this to the left, and this weight's going to get more and more negative. Now I'm going to stop. Now this is interesting. This output is negative. I'm going to make it more negative. So to make this output more negative, well, we have a positive input. So I should make the weight more negative, right? Like a positive times an even more negative number will make this get more negative, this output more negative. But what else should I do? How should I change this neuron's value? Should I make this be negative? Well, think about it. I have a negative weight, and if I made this output get more and more negative, I'd have a negative times a negative, which would be a positive. And that's not what we want. We're trying to make this more negative. So what actually happens is the change that I want for this is negative. And so the change for the weight is a negative change up here times the input, so a positive number, so the weight gets smaller. But in order to see how to change this neuron's value, I need to take the negative change up here, bring it through a negative weight, and get a negative times a negative, which is a positive. And so if I drag this, you can see that that middle neuron actually gets more and more positive. And it just makes sense intuitively. You know, I'm saying, I know I'm throwing all these negatives and positives out there, but if you just watch it, just watch it. Let's start when this is close to here, like a small positive number. I want to make this negative, so I'm going to make this weight negative. I got a negative value down here, so let's just make this negative. There you go, see? So I made this weight more and more negative, and now I want to make this even more negative. Well, if I make this more positive, look what happens. See how the output got more negative? So that's all it's trying to do here. It's just trying to make this get more positive because it's got a negative weighting on it. So there we go. Boom. Pushing this to the left pushes this one to the right, pushes this more positive. All right, but I don't even have to think about any of that. With backpropagation, with this tool, which you can play around with yourselves, you can just drag the thing, and you don't even have to worry what's going to happen. You know, I could say I want this to be positive, I want this to be positive, I want this to be positive, and now everything kind of goes in step. Or you could say, oh, I want this to be negative, and I want this to be positive, and now you have like a snake, right? And so it works with more layers. You could add a whole bunch of layers, and we could make like a snake like this, you know, just for fun. And there you go. Everything's kind of working nicely. All right, so let's solve an example problem with this now. Okay, so let's try this on XOR. Let's like hand train a neural network on XOR. So we're going to have some input neurons, and we're going to actually have 3 because I'm going to turn on biases. So we'll have 3 input neurons. We'll have 3 hidden neurons for the bias, 1 output, and not nearly as much layers there. Okay, so this is our network structure for XOR. We have 2 inputs down here on the left, and these neurons over here on the right, I'm going to consider them as biases. So this one has no inputs to it. You see how it's just a value that I can set. We'll just leave it at 1. And this one has no inputs as well down here. So I'm just going to leave that at 1. These are our biases to the network. Now we have 2 inputs, 2 hidden units, and 1 output. So for XOR, if you remember, 1 and 1 is 0. It's exclusive OR. It only likes one of these inputs to be a 1. Now I'm going to say 0 and -1 interchangeably because we're using hyperbolic tangent. So just think blue is 0 and red is 1. So for 1 and 1, we want 0. Now I can save a training example. So if I tap the A key on my keyboard twice, it's going to save the inputs at whatever value they are and the output at whatever value it is, and that becomes a target value. So for 1, 1, we want 0. For 0, 0 on the inputs, we also want 0 for XOR, so I'm going to save that. For 1, 0, we want a 1. We'll drag that out. And for 0, 1, we want a 1. Now, if I cycle through these by just tapping the key on my keyboard, like I tap A, and that's the inputs and outputs for A, S, that's the inputs and outputs for S, they're all under just a key. So whatever key I tapped will hold the target values for these inputs and outputs. So for 1, 1, we want 0. So I'm going to drag this by hand. Remember, dragging a neuron in this this tool here, this diagram, whatever you want to call it, that does backpropagation. So if I drag this to the left, I'm actually backpropagating a delta up here, and basically saying, well, for 1, 1, I want this output to be a -1 or a 0, right? Okay, so for -1, -1, I want this to be negative as well, right? XOR, it doesn't like when the inputs are the same. And look at that. If I cycle between 1, 1 and 0, 0 on the inputs, and I warned you I would interchange -1 and 0. So 1, 1 and 0, 0, the output is a 0 for XOR. So that's great. Now, let's see what happens if we have a 1, 0. That should be 1. So we kind of destroyed what we had trained this to do before. Like, I had dragged this to a 1 before, but because I changed the weights when I was training on 1, 1 and 0, 0, I messed up 1, 0 as an input. And now look at our 1, 1 and 0, 0. These should both be blue up here at the output, but no, I messed them up by training on that other example. So this shows you that as you train on each a pair of inputs and outputs, you're changing the network's output on your other pairs of inputs and outputs. So that's why you have to make sure that you train on uniformly sampled data in random batches. So you have to see all of your data set, or else you're going to destroy part of the training for other labels as you train on new labels. But we can do it by hand. We can kind of guide and shape the network by hand. So for 0, 0, we want a 0. For 1, 1, we want a 0. For 1, 0, we want a 1. And for 0, 1, we want a 1. So it's looking good. 0, oh, but see, we destroyed it for -1, -1. So we'll go over here, train it. Okay, that should have been a 1. That should be a 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0. And I'm kind of acting like the computer here. So I'm trying to randomly pick examples and guide the network's output to what I want it to be. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1. Now this one's giving me a lot of trouble here, these two pairs. So what can we do? Well, 0, 0, 0, and a 1. We can even go in the lower layers and just kind of mix things up down here. Just to, if we got stuck, we can kind of mix things up. So 1, 1 is a 0, -1, -1, that should be 0. This should be a 1. This should be a 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0. 0, 1, 1 is a 0, 0, 0, 1, 1, 0, 0, 1, 1. Oh, I think we're close. I think we're close. Just be delicate with it. 1, 1, 0, 0. Yes. So we did it. I can push it to the extreme now, I think, a little bit. It would push that one. That should be 1. That should be 0, 1, 1, 0, 0. Yeah, so I can start to train this even more. Now that we've kind of found this distinction point. It should be 1, 1, 0, 0. Okay. So let's run through our examples here. So we got a 0, 0 on the input. That's a 0 for XOR. And we have a 1, 0. That's a 1 for XOR. It's above 0, right, this output. We have a 1 or a 1 0 here. That's still a 1, right? The inputs are different, so it's a 1. And when the inputs are both a 1, it goes back to 0. So we trained this thing by hand. You know, it was kind of difficult, but it's also kind of instructive. You have to be kind of gentle with it. You know, if you push it too far at the start, it's going to be harder to find this separation point to separate these 4 training examples into these 2 outputs. But once they're separated, then you can kind of push it, which is interesting. So anyways, you know, it's these kinds of little moments that this tool gives you that I think are pretty valuable. So I'll leave it to you guys to kind of play around with it. I'll put a link to it in the description. I have it here locally, which I'm playing with, but I'll put it up on my website and put a link in the description so you can play with it. Let's look at just a few more little things you can do. So we have different activation functions. So we got tanh, sigmoid, and you can see the sigmoid curve over there. We got leaky ReLU, which is just a really simple one where it's linear if the input, the weighted sum is above 0, or it's a small fraction of it if it's below 0. And we also have just a straight up linear neural network. So this linear neural network could actually not solve XOR. And I can train this thing a lot faster than by hand. So if you hold down the T key, it'll train on all your data examples. Let's try it. So I'm going to just hit T here. And if you notice, I can lower the learning rate here. It's not able to solve this problem. Linear non-linearity. First of all, that doesn't even make sense, but this shows that the non-linearity is crucial in terms of solving more complicated problems. Otherwise, you can condense all these layers into just one linear transformation. Although with the bias, they aren't exactly linear transformations, so that would take some investigation, but you need like a tanh or a sigmoid for this thing to train. So it's not going to work like 0, 0, we want a 0, and it's just giving us this 0.3. It's kind of going to the average, right? Okay, so let's look at one final thing here, so let's look at one more thing here, which is kind of just fun to see. I refresh the page, and you're going to get a random network to start with. Now, if I change this weight scale, it changes the range that the random weights are drawn from. So if I make this 0, you can see that all these neurons are 0. And if I turn off biases on the right, you see all these intermediate and output neurons are all 0, right? Because regardless of what this input is, the weights that lead up to this neuron are all zeros, so this is going to be a weighted sum of 1 times 0 plus 1 times 0 plus 1 times 0 is 0, right? So now I can't do my trick. I can't change the values of these neurons up here because they change their weight values by using these previous neuron values. So if I want to change this, I need a value back here to work with to change the weight that's going to lead into this neuron. So I kind of have to work my way up from the bottom, and I'll get, I can change this one, and you see how it's using, to increase this value, it's going to add something to all of its weights, and it's going to add a fraction of whatever the value of these neurons are. So I'm going to actually zero out all of these, though. I just want one of them to kind of control this one. So I can zero out weights by holding Command and just touching a weight, and it will zero it out. So if I want to change this neuron's value, look at that, it's going to use the only value that it has access to. Now if I go up to this layer, I still can't change these because there's nothing to work with in the immediate previous layer. But if I go to this layer, now I have something to work with. So I can do some backprop on this neuron. And if I go up to the next layer now, I do have something to work with in the previous layer. And so I can kind of work my way all the way up here. And I've got this whole chain now, this whole link through the network. And if you think of these weights as being in a matrix, then I really only have one value in the matrix here. I only have one weight in the matrix. And I mean, if you think of reality as being the matrix, like a big simulation, well, then I don't even know what we're all doing here. But that's regardless of that. So we have this link through the network, which is kind of cool. And I can kind of dictate what I want the output to be given the input. So if the input's positive, let's say I want the output to be negative. Okay, so now every time that the input is positive, the output's negative, and it's taken on this kind of opposite relationship again, right? Now here's one more cool thing. I'm going to go back to a normal network with starting weights. So there's some starting connections to work with. We'll have some biases on. We'll have one output neuron, and let's do 2 output neurons and 1 input neuron. And we don't need this many layers, and we don't need this many hidden units. Let's get rid of a few. Let's do something cool. I'm going to make like a little grasper. So I'm going to disregard what the values are and just kind of train this thing to do what I want. So, and I'm going to show that there's a complex relationship from this input to this output. So when this input's -1, I want these little guys to be opposites up here, like -1 and 1. It's kind of like a little gripper if you think this is like a little robot gripper. When this is -1. Now this is crazy. If this is 0, and let me save that as a training example. So I'm going to tap A twice. That's my training example here for A. Just give it a name, A, right? Whatever key I tap. Now when this is 0, I want this gripper to be closed. So I'm going to close it by hand. I'm actually doing backpropagation by hand. And we'll save it as a training example. I don't need these training examples, but if I don't want to tweak it by hand a lot, it doesn't really take that much tweaking by hand. But if I want the computer to train itself, I save these training examples. So finally we go to 1 here on the input, and if you notice I've only increased the input. So it's a nice simple just increase, -1 to 0 to 1. I want the gripper to be open again. And we'll save that. Now let's see what happens if I just run through this now. So it seems like it kind of forgot my training, right? Or I destroyed my earlier training. So -1, I want it open. 0, I want it closed. Let's just try to train it by hand a little bit. And 1, I want it open. And 0, I want it open. I mean, -1, I want it open. 0, I want it closed. And 1, I want it open. I want it open, closed, and open. So we're sort of getting somewhere, but let's just train this thing. I don't have all day here, right? Let's just train this with those training examples by holding T. So it's looking pretty good here. So let's see how this thing works now. So when this is -1, it's open, right? And as I increase to 0, it's closed. And then as I keep increasing, it opens again, which is kind of crazy. It's almost like this is like almost like a parabola, a graph of a parabola, and this is the input, right? It kind of is negative, and then it goes up, positive, and then comes back negative. So negative, and then it goes up, and then it comes back down. And over here on the right, we've got positive, and then it kind of dips, and then it comes up. So really, I've kind of trained this complicated function. This whole thing is just one function. This is the input. These are the outputs. And I've trained this complicated function just by hand, by dragging these around. And that's all the training does either. You know, when I train on an example, if I train on the D labeled set, that's going to set this value to be 0. You can see this gray ring is where it's going to be set when it's training. So this becomes 0. this is going to get pulled to 1, and this is going to get pulled to -1. And it does the same exact pulling that this pulling does. And it just, you can see each random, it runs through all the random data pairs. So we made this little gripper, which I think is kind of cool. And finally, if you want to see how it, this tool kind of shows you how it works a little bit. So we can try to parse how this thing is working. So from -1 to 0, which neurons are moving the most? Those are going to have the most effect on this thing, right? So from -1 to 0, it looks like this neuron right here is doing a lot of action. It's pulling these guys closer together, likely. So from -1 to 0, that one's moving like crazy. Now what happens with tanh is this thing is gonna bottom out. No matter how much more negative its input gets, you can see in that graph, its output is just going to kind of remain static. It's not going to be completely static, but its output's not going to be changing very much. It's going to be squashed to -1, right? So from 0 to 1, what neuron is moving the most there? Well, can you see it? I would guess this neuron over here, right? So from 0 to 1, all of a sudden that guy is flying, and I bet you it's having the most effect on these two outputs. So really this neuron goes through these intermediate ones, which it's harder to say what the intermediate ones are doing. But once it goes through those intermediate ones, really we only have 2 neurons up here that are really doing anything. So from -1 to 1, this neuron's doing everything. Meanwhile, this one is saturated over here. If you look at it, look at how completely saturated that is. It's way over on that plateau of hyperbolic tangent. So this one is saturated. This one's not doing anything. But from 0 to 1, look where we are. We're at 0. We're approaching the point where this becomes almost, the output becomes almost linear. And from 0 to 1, that one is doing all the action, right? So this one's doing all the action while this one is saturated over here on its little negative plateau. So I don't know, how useful is knowing that? I think it's just kind of cool. It gives you a better idea of what these things are doing, how they're training, how they're combining. They're really combining weighted averages of a bunch of hyperbolic tangent curves, right? And you can make any kind of shape you want if you combine a bunch of tangents or sigmoids or whatever nonlinearity you use. So you have 2 outputs, 1 input. It's kind of cool. You kind of get like a physical feeling for what this network is doing. So I think that's about enough for this tool. I'm going to put it up on my website, and I'll put a link in the description so you can check it out. And yeah, thanks for sticking through this. I'm sure it's quite a long video. So I'll see you guys in the next video. Thanks again.